Okay, I'm going to go ahead and get started. Welcome to day 3 of the Introduction to Quantum Mechanics short course, lecture 5 out of the 6-lecture series. Yesterday, we talked about the different forms of the Hamiltonian, okay, and on day 1, we gave a very top-level overview of the information that you need to do these calculations on the molecular scale and the form of the wave function. Okay. The lecture today is going to go into different types of calculations that you can use to investigate excited states, okay, different methods. There we go. Okay, so if you are interested in calculating the properties of excited states, excitation energies generally, there's a number of different methods that you can do with these calculations. If your excited state of interest has a different spin or a different symmetry, then that simplifies calculating the excited state energy. Okay, so for example, in the hands-on session that we did yesterday morning, we were looking at O2 triplet ground state and its first singlet excited state. Okay, so that was reasonably straightforward to calculate. It's a little bit difficult to calculate accurately, but reasonably straightforward to calculate since it has a different spin. So you just set up a triplet calculation and you set up a singlet calculation. You tell it the spin state, okay, and it will give you the energetics. If you wanted to go to the next singlet excited state, things get far more complicated. Okay, you have to use different methods to calculate the excited state for when you have the same spin, okay, or the same symmetry. Okay, so the other possibility is if your molecule has symmetry and you're looking at and you have unpaired electrons. So for example, osmium dicarbide cation is in C2v symmetry. It has one unpaired electron. So you can have and easily calculate 4 different wave functions, the A1, the A2, the B1, and the B2. So these 4 different states, one should be the ground state, and the other 3 will be excited states. Okay. So there may be excited states that are in between, but these are the most readily to calculate, the easiest to calculate when you have symmetry and unpaired electrons. Okay, so we'll get into this a little bit more. This is the symmetry table. Okay, so if you are unfamiliar with symmetry, if you go back to, I believe it was lecture 1, there was a link to a symmetry tutorial that goes through these functions. And like I said, we're going to talk about that a little bit more during this lecture. Okay, so let's look at a simple example. Let's just look at the water molecule. And let's pretend, just for fun, that we want to do triplet state of molecular water. Okay, so if we want to do the triplet state, we want to see what the overall symmetry is of the wave function, then we need to know what symmetry the unpaired electrons, the orbitals that the unpaired electrons occupy. And from that, we can determine the symmetry of the overall wave function. So let's say that we have an electron that's in an A1 orbital and a B1 orbital. Okay, so if you take the unsymmetrized basis set, looks like this, and if it's symmetrized, then it'll look like this, and you can categorize them. This has B1 symmetry, these have B2 symmetry, okay, and all of these have A1 symmetry. So back in lecture 1, I mentioned that if we do have symmetry for our molecule, it decreases the computational cost. Okay, every time you have a symmetry operation, you have your computational cost. Okay, and this is the reason for that. So remember that all of our calculations are in matrix form. We have a matrix of the orbitals, okay, and we have the Fock matrix, and the energy matrix. And when you have symmetry, it can transform this matrix from a dense matrix where we have a lot of values, in the matrix to something that is symmetric, where we have a lot of zeros. And if you draw a diagonal here, this upper diagonal is going to be the same as the lower diagonal in the matrix. Okay, so that's how it decreases the computational cost, because it symmetrizes the matrix of elements, and it doesn't have to compute as many of those 2 electron integrals. Okay, so once we have this symmetrized, let's say I put an electron in an A1 orbital, it could be any one of these, okay, and a B1 orbital. This is the only one that is B1 in character. I have to come to my C2V point group table, and I take my A1 and my B1, and I take the cross product. So I multiply 1 by 1, okay, 1 by -1, 1 by 1, and 1 by -1. And what I end up with, I got shifted, is 1 minus 1, 1 minus 1. So if I go to my point group table, B1 is the one that matches that. So it's 1, a -1, a 1, and a -1. Okay, so my overall wave function symmetry is B1. Now, convention says that orbitals are assigned lowercase letters and wave functions are assigned uppercase letters. But you see that a lot of people won't follow that convention, okay? But like I said, the standard convention is symmetry assignments to orbitals will be lowercase, and symmetry assignments to the wave function, the overall wave function, will be uppercase. Okay, so let's do another example. Let's say I want to put an electron in B1 and an electron in B2. I go through and I do my multiplication with the B1 and the B2, and I'm left with an A2 wave function, okay? 1 times 1, -1, -1, right? -1, 1, 1, -1. So my A2 state, right here, 1, 1, -1, -1. Okay, so if you have unpaired electrons and you have symmetry, you can choose what the symmetry is of those orbitals to put the unpaired electrons into. Okay, and then you can define what the overall symmetry of the wave function should be. Okay, and then you can sample all of the symmetry elements in their occupation for the different excited states. So this is an output file, part of an output file from Gaussian, just as an example. Okay. So one of the things that I mentioned in the first lecture, on the last slide, I believe it was that when you're doing unpaired electrons, you're doing an unrestricted calculation, and often people will look at the highest occupied molecular orbitals and assume that they're the unpaired electron orbitals, okay, or the orbitals that have the unpaired electrons, otherwise known as the SOMO, singly occupied molecular orbitals. And that is not always true. Okay, one of the first things that you can do is look at the orbital symmetry assignments. So if your molecule's in symmetry, Gaussian should assign the symmetry of the orbitals. Okay, so you can come in here and look at here's the alpha occupied orbitals and here are the beta. So spin up, spin down. And you can just cross them off by symmetry. Okay, so now you'll notice that my unpaired electrons are going to be an A1 and a B1. Okay, with the B1 is definitely not one of the higher occupied molecular orbitals. Okay, so the other thing that I want to point out here is I actually don't know which one of these A1 orbitals is the singly occupied. Now I know I crossed this one off, but this is not necessarily the singly occupied. The only way for me to truly know which one of these is singly occupied is by visualizing the character of those 2 A1 orbitals, these 2 here, and see which one matches this one. Okay, that will tell me which one of these is actually singly occupied. Okay, so if I have a B1 and an A1, B1 cross A1 gives me a triplet B1 state, which is what is listed here for my wave function. Okay, so let's say we want to sample the other electronic states for this triplet state. let's say that we want to do the triplet A1 state. Okay, so this wave function from this calculation came up with a triplet B1. If I wanted to get the energy of the triplet A1 state, I could swap orbitals around, the occupied orbitals, okay, or the unoccupied orbitals. So I get occupation of the orbitals that will lead to a triplet A1 state. Okay, so in Gaussian, you can use the guess equals read alter. Every program has their own way of determining which orbitals are going to be singly occupied or doubly occupied. Okay. The main thing is you need some kind of a starting guess. Okay, so usually you do a calculation, you get a starting guess, and then you manipulate it from there. Okay, or you can tell the program, I want to make sure that these are the singly occupied symmetries, and it can try to fill it for you. Okay, so there's multiple ways of doing it. Generally, you start with an already converged wave function, and then you manipulate it. Okay. So if this is what I want to do, I just need to look at this and say, okay, if I swap these beta orbitals, this one now becomes occupied, and this one is now unoccupied. Okay. And with that, I will end up with a triplet A1 state. So here is an input file that shows that, where I have the guess equals read and alter. That means I already have a converged wave function for the triplet B1 state from a previous calculation. I'm reading in that wave function, okay, and I'm altering it. I'm skipping alpha swapping, and I'm adding in beta orbital swapping. So with beta orbital swapping, I'm swapping orbital 4 and 5, okay, which are the ones that I pointed out above. I never assume that I've either set it up correctly or the program is doing it correctly. So I always like to double check in the output file to make sure that it's swapped what I think it has. It says that it swapped orbitals 4 and 5, which is what I wanted. Okay. And then I can come here and I can look at the actual orbitals that are listed and their symmetries. And it shows me that the initial guess for my wave function now is a triplet A1, which is what I wanted. The other thing that I want to point out is that for a lot of these programs, your symmetry of your starting wave function may not necessarily be the symmetry of the final optimized wave function. Okay, this is also code dependent. So if you check and make sure that the starting symmetry is correct, please make sure that the ending symmetry is correct. And it didn't fall to some other orbital occupation, break symmetry, do things like that. Okay, so what you should see is something at the beginning that's a triplet A1 and at the end, because remember, this is an iterative process where it's trying to optimize the wave function. Okay, so if I wanted to double check that, I would come through and I would cross them off, right? And in this case, it does look like the two highest occupied molecular orbitals are the singly occupied, at least at the beginning. That's not necessarily going to be true at the end of the calculation. Okay. Okay, so like I said, if you have different spin states for your ground state and excited state, you just need to do a standard calculation changing the spin state, and then you can get the energy gap, okay, how much higher in energy the excited state is. So that's fairly straightforward. The quality of the results depends on the level of theory that you're using and the complexity of the molecule. If you have symmetry for your molecule, okay, you can have the same spin state and you can converge fairly easily on the different symmetries for the wave function that go with the point group. So C2V has 4 symmetries available to it, so you can get the ground state and the first 3 excited states in that point group fairly easily with a standard calculation. You just need to manipulate the orbital occupation to get the different symmetries. Okay. So if your molecule does not have those differences from the ground state to the excited state, there's no change in spin, there's no change in symmetry, then you need to use some other method. Okay, some of the other methods that are available, CIS, this is part of the configuration interaction that we talked about in the lecture yesterday morning. It includes dynamic electron correlation, okay, and it is variational, but CIS only affects, it doesn't directly affect the energy of the ground state, okay? It doesn't mix with the ground state, so you don't correct the energy of the ground state, but what it can do is calculate the energy of excited states. So if you do a CIS, single excitations, you get Hartree-Fock quality results of the excited states. Okay. Okay, random phase approximation is similar to this, okay, but it includes some double excitation, so it includes some of the dynamic electron correlation. CIS parentheses D is CIS, which is, like I said, Hartree-Fock quality results for the excited state, but it uses perturbation theory, okay, second order perturbation correction to incorporate dynamic electron correlation correction of the energy of the excitation. So just correcting the energy of the excitation, okay? The one that you'll see in the literature most often for calculating excited states, I'm looking at UV vis spectra, things of that nature, is time-dependent density functional theory. Okay, and that's because it incorporates the dynamic electron correlation for a reasonable computational cost. Okay, so let's talk a little bit about CIS before we go into the time-dependent DFT. So as I mentioned, CIS gives Hartree-Fock quality results for the excited states. This is just an example for benzene with a Hopel double zeta basis set with diffuse functions on the carbons, not the hydrogens, and a polarization function on the carbons, a D function. Okay, so this is using various methods. So this is comparing CIS, the random phase approximation, density functional theory, the time-dependent DFT, and this is using so this is hybrid, this is GGA, and this is the LDA that we talked about yesterday afternoon, okay? And here are the experimental values. Okay, so it's showing, you know, the different types of excitations, the symmetry, and the deviation from the experimental value for the different levels of theory. Okay. So you can see that, you know, some do better in one than the other, but DFT tends to overall get the best results for the computational cost. Time-dependent DFT tends to get better results overall for the computational cost. Okay, so how do we read the result of these excited state methods? So one of the ways that these calculations will provide the results is they give you contributions to the excitation, okay? They give you the symmetry of the excitation, the energy in whatever units that program uses. Gaussian uses EVs in nanometers. And then it gives you something called the oscillator strength, okay? F equals. The oscillator strength is proportional to the extinction coefficient. It is not the extinction coefficient. It's proportional to the extinction coefficient. And these calculations are only done to first order. Okay, so if you have a small excitation and it's forbidden to first order, then it will have an oscillator strength of 0. So you may see a weak peak experimentally that could have an oscillator strength of 0 computationally. Okay, and that's because these calculations only calculate to the first order. So if it's spin forbidden, so if you have a different spin, okay, or if it's dipole forbidden, there's no change in the dipole, then you have 0 for the oscillator strength. Okay, so you have higher order effects that you will see experimentally. Okay, so weak peaks that you see experimentally may not show up with an oscillator strength computationally. Okay, so the other way to read this is looking at what orbitals are contributing to the excitation. So when you come to this, it's a linear combination of excitations. So what you want to do is look at the largest coefficients and look at the character of those values. So here's an example, excitation 1 for benzene. It's a pi to pi star. And it's a combination of the highest occupied molecular orbital to some higher energy unoccupied, right? sorry, the highest occupied is this one, and the highest occupied molecular orbital -1. So we have the HOMO and the HOMO -1. Okay, so this excites to this pi star, and this one excites to this pi star. This is the stronger contributor here, right? The 20 to 27. And then there's a weaker contribution from 20 to 28, which I don't even have shown. Okay, so you look at these as the large ones, and you take a look at the character. So we have a pi to pi star transition that are equally contributing to this overall excitation. It's not a single orbital necessarily that is exciting to another single orbital. It's a linear combination. And now this would not be observed to first order, right? The oscillator strength is 0. So I like to point this out because what you see experimentally as the first observed excitation, okay, the large oscillator, or the one that has strong a peak extinction coefficient, is not necessarily the first calculated excitation. The calculation is going to calculate all of the excitations. Okay. But experimentally, you're only going to see the allowed excitations. Okay, so there's a question in chat. We must always have a polarization function because we're dealing with unmatched electrons in excited states. When you're doing excitation calculations, you should definitely have polarization functions, and you might also want to include diffuse functions. Okay, mostly because we're dealing with excited states and you substantially polarize the density. And in the excited states, the density is usually further from the atomic center. Okay, so when you're exciting, your polarization functions, the higher angular momentum functions contribute more. So yes, you are absolutely correct. Okay, so I like to show this as an example of what you can do with time-dependent density functional theory. You can see the experimental spectra for these 3 species on the left. Okay, and this was a mixture of compounds, and they weren't quite sure which one was which. This is the time-dependent DFT result for these compounds. And you can see, to me, how well they match. This is very, very good, okay, correlation from the calculations to the experimental. It normally does not come out this nice. Okay, so this is a really, really spot-on result for time-dependent DFT. Usually you have more variation, but you can still see that there are differences, right? So, you know, there's overlap here where we don't have it here between the experimental and the time-dependent DFT, but the overall character looks the same. There's still, you know, shifts from the calculated to the experimental. It's not a perfect match, but it's really, really nice. All right, so let's see. I'm actually missing a slide in here. Okay, let me point one thing out here, and let me see if I can. I want to annotate on here. Okay. When you do a time-dependent DFT calculation, the only thing that you get out of the calculation is, you know, the location of the peak, right, where the excitation is, and the oscillator strength. So what's shown here, like for the green line, okay, what's shown here is a simulated spectra. Okay, and that means it calculates based on, it uses an equation to convert the oscillator strength to an extinction coefficient. You have a broadening variable that you can put in there to see how much broadening there is, but all you're getting from the calculation is the location of the peak and the oscillator strength. And then you have to simulate the spectra. Okay, and Gaussian does that for you. There's a lot of codes that will do that for you. Okay, when you load the result. But I want it to be clear that the calculation itself, the output file doesn't have this type of spectra in it. The calculation only has these locations and oscillator strength values. Okay, some other excited state methods that are available, but have a substantially higher computational cost. There's something called CIS, Symmetry Adapted Cluster Configuration Interaction. There's a lot more that you have to tinker with to use this. So just like with the CAS-SCF calculations, you have to choose some of the orbitals. They have to be symmetry adapted. So there's a few things that go into this that make it more complicated to set up and run. Equation of motion, CCSD. As you know, CCSD has really high computational costs. So unless you're looking at a pretty small system, equation of motion, CCSD, which includes couple cluster singles and double excitations to include that dynamic electron correlation, is computationally intensive. So again, you would only be applying this to a reasonably small molecule. So depending on the resources that you have available. You can also use the multi-reference methods. The optional part of the molecular oxygen hands-on session that you had walked through looking at excited states for the CAS-SCF calculations. Okay. If you want to include the dynamic electron correlation, then you would do CAS-PT2, okay, where you add on the MP2 correction to the energies. And then you can also use something called multi-reference configuration interaction to improve the results of the excited state. But again, these are not for the faint of heart. They require a lot of intervention by the user, choosing active spaces, cutoffs, things like that. So you could definitely perturb your results and get odd results or incorrect results if you're not careful. Okay, so I want to mention something called semi-empirical calculations because it falls into a method that can do excited state calculations at much lower computational cost. It's a semi-empirical calculation. Semi-empirical calculations are below Hartree-Fock. They're not on the ab initio range. They're heavily parameterized, okay, with experimental data. It is solved iteratively. It's still based on the Hartree-Fock formalism, but instead of calculating the very, very expensive 2 electron integrals, those are replaced with parameters. And those parameters are based on fundamental properties of the orbital energies. Okay. All right, so it doesn't have to directly calculate these 2 electron integrals, just replaces it with a parameter. It is parameterized to reproduce heats of formation. So commonly used semi-empirical methods that you'll see in the literature when you do see them, AM1, PM3, PM7, but what we're going to talk about is ZINDO /S. This is specifically parameterized to calculate electronic spectra, and it was primarily designed for organic species. I'll skip that. Okay. So ZINDO-S can do very large systems. So that's what is shown here, if you're interested in doing excitation spectra. But generally, you need to calibrate this. Okay, so in this paper, what they did was they took a small section of this large species and calculated with time-dependent density functional theory or some higher level calculations, so melam and melamine. And then they compared it to the ZINDO results. Okay, so they calibrated the ZINDO level of theory against a higher level of theory for a smaller model. And then they scaled up with the lower level of theory. And this is very common practice. You take a small segment that is a reasonable description of a part of your big system. And you do a higher level calculation on it. And then you do that same small system with the low level. And if you get consistent results, you scale up with the low level of theory, making the grand assumption that scaling up is still going to give reasonable results. And most of the time, that is a reasonable assumption. Okay. So it would be very difficult and computationally intensive to scale up to these things with time-dependent DFT. Okay, you could do this, but it would take a long time and you would have trouble converging all of these different excitations. It's a lot of excitations. As these excitations get closer and closer together, you have to do, 50, 100, 150, 200 to move up in the excitation scale. So it's very beneficial to be able to use this lower level of theory to scale up to a much larger system. So you can compare the different configurations as they have done in this publication. I just want to briefly mention there's another program called Fenske-Hall, developed by Michael Hall at Texas A&M University. And this is available from this webpage. It's incorporated in a Windows program. And you can calculate molecular orbitals for transition metal containing species like that, very fast, if it converges. It is an iterative process. Okay, it's not going to do geometry optimizations, and it doesn't actually calculate the spectra, but it will give you orbital energy levels, which you can try to map to whatever experimental data you have. So Fenske-Hall is based on extended Hückel theory. Okay, so it replaces the diagonal terms with these adjustable tuning parameters. Okay, and you can get molecular orbitals and their energetics quickly. Okay, so if you're interested in getting an initial estimate from these, you might want to take a look at that. Extended Hückel theory will also let you do solid state if you get the right code, and you can calculate band structures from it. No geometry optimization. Okay, this is static geometry, so you have to have a good starting geometry, but then you can get the wave function from it and density of states. Okay, so during the hands-on session, we're going to be calculating excited states. But in the last few minutes of this lecture today, I just want to mention these composite methods that can be very useful if you're doing first, second row main group and maybe first row transition metals, because it does have parameterization in it. Okay, so one of the things that we mentioned in the lecture with the Hartree-Fock theory was the Hartree-Fock limit. The Hartree-Fock limit was, with the ab initio level of theory Hartree-Fock, the best result that you can get with an infinite basis set. Okay, so that would be running up this line here, where you have the Hartree-Fock at minimal basis set all the way up to an infinite basis set. Okay. Adding in dynamic electron correlation would be going up the ab initio series to full CI. And that's including more and more of the dynamic electron correlation. Okay, this is along the lines with the minimal basis set. Okay, what we'd really love to do is get the exact energy where we have an infinite basis set and full CI. But this is really out of reach. Okay, and even walking along this line where we're increasing the level of theory and the basis set becomes computationally out of reach. Okay, so what the composite methods do is they try to calculate the quality results as if you did this calculation by walking along this line and walking along this line in a simplified fashion, okay, and then getting results that look like this or have the quality as if you did this really high level calculation. Okay. So the general premise of this method is walking through these types of steps. So you have to select a level of theory for your geometry optimization to get a good geometry. You select a level of theory for the 0-point energy correction. Remember, when we do our optimizations, we're looking at a potential well, and we're all the way at the bottom of the potential well. Okay. So frequency calculations are also more computationally intensive, so that's why they originally split up the geometry optimization and the calculation to get the 0-point energy. Okay. And then you select a level of theory for your reference energy, where you're doing a single point energy calculation. Remember, a single point energy calculation is you don't change the geometry, you just correct the energy, okay? Because the geometry is not as sensitive to the level of theory as the energy. And then you perform a variety of single point energy calculations, increasing either the basis set or the level of theory or both. Okay. And this is supposed to have a linear combination of increasing contributions from basis set truncation and the dynamic electron correlation truncation. And then the last one here is this estimate of the spin pair correlation energy. Okay, so you have that dynamic electron correlation that is really hard to get accurate. Okay, so this is a parameterization that's added in. And that's why you can't apply these methods across the entire periodic table, because you have to have this estimate spin pair correlation parameterization for that element. Okay, and it's not available for all elements. Okay, so this just shows the level of accuracy that it can get. And this is usually for thermodynamics. Okay, most of what it's looking for is delta G of reaction or delta H of reaction. That's what it was originally parameterized for. And like I said, mostly first row, second row, main group, and some transition metals. Okay. So this is getting down to what's considered chemical accuracy for the data set that they were looking at. Okay, so I think this data set has, can't remember how many molecules it has in it, but I'm pretty sure it's over 100. Okay, so they've started with the original implementation up here at about 1.5, and they've in G4 method they've gotten down to chemical accuracy for their data set. Okay, and this is the mean absolute deviation. So there are outliers that do not fall within that data set. So there's a number of different methods out there for this. They're still computationally intensive, but not as intensive as if you did the really high level calculation with a very large basis set. Okay, so the last thing that I want to mention in this lecture is Koopmans Theorem. So Koopmans Theorem says that the energy required to move an electron from a closed shell atom or molecule is well approximated by the negative of the orbital energy that is being removed from. Ergo, the first ionization energy is approximately equal to the negative of the highest occupied molecular orbital theory. Okay. This is not true for electron affinity. You can't say that the electron affinity can be well approximated by the energy of the unoccupied orbital. Okay, and this is because the LUMO, the lowest unoccupied molecular orbital, is not optimized like the occupied orbitals. When the Hamiltonian is operating on the wave function, it's optimizing the occupied orbitals. And the virtual orbitals are the ones that are left over. Okay, the LUMO is reasonable in character. Okay, but as you go up in the orbitals, you'll notice they start to look weirder and weirder. Okay, very diffuse, very poofy, and the more basis functions you have, the more unoccupied orbitals you have. Okay, because the Hamiltonian is optimizing the coefficients for the occupied orbitals, not the unoccupied. So this also means that you can't just look at, if you have experimental spectra, and you know that the first excitation that you're viewing is the HOMO to LUMO transition, you're not going to get good energetics if you just look at the HOMO energy and the LUMO energy. Okay, that gap is usually too big compared to what you have experimentally. And that's because when you excite the electron, okay, the wave function for the excited state is going to relax, right? Because now that you've taken an electron and separated them, you take it out of an orbital and put it into another orbital. So you get some relaxation, which will usually close that gap, okay, from the occupied orbitals previously and the new occupied orbital. So it's an estimate that you can use to look at the character and the excitation energy, but it's not going to be a high quality excitation energy. It's definitely going to vary from the experimental. And that's where the other excited state methods come in when you do CIS, time-dependent density functional theory, because it's actually looking at the excitation and the relaxation from that excited state. Okay, okay, so this is the hands-on that we're going to be doing, is looking at excitation calculations and analyzing those results. So let's go ahead and take a little bit over a 5-minute break, and we'll start the hands-on session at 10:50. Okay, let's get started with the hands-on session. If you haven't done so already, please log into your VD Portal account and get a new desktop if yours is not already running. I'll give you just a second to do that. Okay, so let me give you an overview of the hands-on session 5. And once I do that, you might want to go back and check the result of your onion calculation from yesterday. See if it completed successfully. And if it did not, we should have time during this session to revisit that if you need some help with that. Okay. Okay, so if you go into your day 3 folder, which you should have on your desktop, you'll find the PDF for today's assignment. So what we're going to do is we're going to look at the excitation spectra of a fairly small molecule, acrolein. Okay. I invite everyone to go look at the structure posted of acrolein on Wikipedia. Okay. Because what they have on Wikipedia is the wrong conformation. They have the high energy conformation for acrolein. So I always like to point this out because it's been like that for years and years and years. And there's no designation as to why they have listed the higher energy conformation for acrolein. But I don't believe everything you read on Wikipedia, right? Always go to use your background knowledge and always go deeper into the subject. Wikipedia is a great place to start. I love Wikipedia, but it's never the place that you want to stop. Okay, so we're going to calculate the excitation spectra of acrolein. You're going to be drawing this in Gauss view. Okay, so you'll be using the drawing tools in Gauss view to draw acrolein, and I've given you some hints here on how to do that. Okay. I would suggest that after you draw your acrolein, go ahead and send me your view only link so I can take a quick look at it to see whether or not you've drawn the right conformation of acrolein. Okay, so your double bonds, your carbonyl, and your ethene fragment should be trans like this, okay, not cis. And depending on how you draw it, you might end up with one or the other. All right, so we're going to be doing this with both configuration interaction singles, which is like the excited Hartree-Fock results, ZINDO, which is that semi-empirical method. We're going to correct the energy of the excitation using CIS parentheses D. Okay, so when it comes to CIS and CIS parentheses D, the oscillator strengths are CIS level. But with CIS parentheses D, you get corrected energies below the CIS result. Okay? And then we're also going to do time-dependent DFT. Okay, using 2 different functionals, I believe that, hold on, let me check that. All right, so we're going to do this to calculate the UV-vis spectra and compare it to the experimental. So you'll notice the range here. Okay, we have a big giant peak here and something smaller here, and this is on a logarithmic scale. Okay, so notice this is a logarithmic scale. So this is a gigantic peak, and this one is very small. Okay, so this is the first observed excitation that we're going to be looking at. Right, so I have here your instructions on how to draw the molecule, okay, and what level of theory we're going to use. So we're going to do an MP2 optimization using this Popel style basis set. Okay, we're going to be doing it without the diffuse function, so just the polarization function. Okay, so we're going to do that with the geometry optimization at the MP2. I'm going to walk you through drawing it. You're going to save your input file, and then you're going to run that calculation. Okay, now notice I didn't give you much in the way of details about how to set up the level of theory and basis set. I want you to try to do that on your own this morning. Okay, go back and look at your other input files and what we have done previously and see if you can do that on your own. Okay, and prompt me if you get stuck. Okay, so all I can say is that we're going to do MP2 for the level of theory. This is your basis set, and I want you to do an optimization. And then after you do the MP2 optimization, we're going to copy the files over, okay? And then you're going to do the excitation calculations. So I have given you the input files for each one of these, the ZINDO, the CIS, the CISD.com. Can somebody remind me why I didn't do CIS parentheses D.com? Since the level of theory is CIS parentheses D. So why wouldn't I call my file name CIS parentheses D.com? Right, special characters, okay? Parentheses are a special character and Linux doesn't like them, okay? It uses them for other things. It's not that it doesn't like them, it loves them. It just uses them for other things, so you can't include it as a file name because it's special, it does other things, okay? Okay, the other thing that you'll notice that I've included in here is a keyword called 50-50. What this means is it's doing 50 singlet excitations and 50 singlet to triplet excitations. Okay, so half of the excitations will be singlet to singlet and the other half will be singlet to triplet. Okay, singlet to triplet excitations are spin forbidden. So what will their oscillator strength be? Remember, the oscillator strength should be proportional to the extinction coefficient, and this is only to first order. So for all the singlet to triplet excitations, can somebody tell me what the oscillator strength would be? It should be a value 0 or not 0. Okay, so let me go back and touch on that topic again. So these excitation calculations are only looking at the excitation to first order, so dipole allowed or not. Singlet to triplet excitations are spin forbidden. You have a change in spin. You may observe them experimentally, but that's a higher order effect. So the calculation is always going to give you, for these levels of theory, an oscillator strength of 0 if it's forbidden to first order. Okay, if it's not dipole allowed, if it's spin forbidden. So all of the singlet to triplet excitations are going to have an oscillator strength of 0. Okay, but I want you to see that, so I'm having you calculate it. So my next comment would be, why would we even bother calculating singlet to triplet excitations if all of the oscillator strengths are going to be 0? And that may be because experimentally we may have some weak peaks that we think are the spin forbidden transitions, okay, or where they have intensity stealing, but they're strictly dipole, not dipole allowed, okay? So you may have some weak peaks that you may think are being contributed by those not allowed to first order excitations. And you can still investigate those by including the 50-50 and looking at the location of the excitations and trying to match them up with what you're seeing experimentally, okay, even if it doesn't have an intensity listed. Okay, so you're going to go through and do all these excitation calculations. Okay. It explains that you're including geom equals check keyword to read in the geometry. Remember, we did the geometry optimization at the MP2 level of theory, and that's what we want to use for our excitation calculations. Okay, and then you're going to want to submit each one of these calculations. So you have to make a copy of your MP2 checkpoint file for all of the excitation input files, right? Calculations, because we're going to be reading the geometry from it. Okay. And then I walk you through how to analyze the results from the log file. If you're looking at the excitations, the excited states, you can use VI or you can use something else, but basically what you want to look for is F equals, and F equals should take you to the right section, okay, of the log file. So you want to look at the ones with the larger extinction coefficient, the larger coefficient in front of the orbital excitation, and then you can visualize those molecular orbitals to see what types of transitions are involved. Now remember, the first calculated excited state is not necessarily the first observed excited state. Okay, they're two different things. All right, to simulate the spectra, you can load each one of these in Gauss View and look at the spectra. But if you want them overlaid, it's another story. Okay, so I have a little program that I use and have used in the past called SynSpec. I found it eons ago, but it's very useful. And I have a little script called plottit.bash, which will process all the results for you and generate input files to plot with new plot. Okay, so if you run, once you get done with all of your excitation calculations, you can run this plottit.bash and it will give you new plot files. Okay, new plot is a graphical program, or it's a command-driven program that will do plotting inside Linux. I strongly encourage everybody to try it. It really speeds up analyzing results when you're running things on Linux. So you don't have to transfer the files back to your desktop machine, bring it into Excel and plot it in Excel. Okay, so here are the commands to plot within new plot. You can put this in a file and run it, or you can just type them in either way. And it will show you an overlay and generate JPEGs for the overlay. So if you want to visualize the image file that it's created, you can use IFGNOME for that, EOG. Okay. And then we're going to compare that with the experimental spectra for the different calculations that were done. Okay. And yes, we did do two different DFTs, one at B3LYP and the other one using the CAM B3LYP, which was designed more of an excitation spectra. All right, so that's the overview. I'm going to leave you to try to set up your MP2 optimization. And if you run into problems, please prompt me in chat and send me the view-only link and I will help you troubleshoot. Please be very careful about the way that you draw your acrolein. Okay, make sure you have the right conformation. Okay, so I'm going to stop recording now and we'll get to work.